All right, today we're going to dive into a process you absolutely see every single day, but it's so advanced, it's actually shaping the future of technology. It's a technique that can make a car stronger, a solar panel way more efficient, and even a medical device safer. Really, it's all about teaching materials how to behave.
So let me start by asking you a question. What could these three very different things possibly have in common? You've got a heavy-duty car door, a high-tech solar panel, and a plain old license plate. On the surface, they seem totally unrelated, right? But they are all connected by one single fundamental process. Any guesses?
The answer is embossing. It's the art and science of pressing a design or a texture directly into a material. And trust me, once you know what you're looking for, you are going to start seeing it absolutely everywhere. It's like this physical language we use to write instructions right into the world around us.
Okay, so let's start with what you already know. You've come across embossing thousands of times in your life, probably without ever giving it a second thought. It's kind of like the hidden texture of our world.
You know that satisfying raised lettering on your bank card? Yep, that's embossing. The cool, intricate pattern that gives a leather wallet its character, that's embossing too. Even, and get this, the subtle, quilted pattern on tissue paper is a form of embossing. It's an instruction that's been pressed into the material to make it softer and more absorbent. It's this amazing technique that adds detail, function, and just feel to the stuff we use every day.
All right, so we get what it is, but how does it actually work? I mean, how do you press a super precise pattern into something as tough as steel or as delicate as paper? Let's break down the toolkit.
One of the most common methods is called hot embossing. And honestly, the easiest way to think about it is like a very, very precise and powerful waffle iron. You take a material, often a plastic that gets soft when it's heated, you warm it up just enough to make it pliable, and then bam, you press a pattern mold right into it.
Now, what's brilliant about this whole process is the sheer control it takes. First, you have to heat the material just enough to make it soft, but not so much that it just melts into a puddle. Then comes the press, which applies the exact right amount of force. But here's the really clever part. You cool the whole thing down while the pressure is still on. That's what locks the new shape into the material's memory, so when you pull the mold away, you're left with a perfect, permanent copy.
Now, conventional hot embossing, it works, for sure, but it can be kinda slow, sometimes taking minutes for just one cycle. But, of course, innovation is changing the game with stuff like ultrasonic embossing. Instead of slowly heating up the whole material, this uses high-frequency vibrations to create intense, focused heat almost instantly. This slashes the process time from minutes down to just seconds, or in some cases even milliseconds. That's a huge leap.
And this right here is where embossing goes from a simple manufacturing trick to a truly transformative technology. Because this same basic idea isn't just for making patterns we can see and feel. No, it's being used at scales that are almost impossible to wrap your head around, from massive industrial parts all the way down to the nanoscale.
So let's start big. At the macro scale, engineers use something called near-surface embossing. By pressing these incredibly precise patterns into high-strength steel, like the kind you'd find in a car door, they can strategically make the metal harder in key spots. This makes the part stronger and way better in a crash, all without adding a single gram of extra weight.
So in this case, the embossed pattern isn't for looks, it's a command. It creates something called work hardening. You know how a paper clip gets stiffer if you bend it back and forth a few times? It's the same idea. The process literally tells the steel, become stronger right here, which leads to lighter and safer cars.
Okay, that's already impressive stuff. But what happens when we take this idea of pressing instructions into a material and we shrink it down, way, way down? Well, this is where embossing stops being just a tool and starts building the future.
So, just how small are we talking? This small. Using these techniques, scientists can now emboss tiny channels into a polymer that are just 188 nanometers wide. To put that in perspective, a single human hair is about 80,000 nanometers thick. We're talking about making features thousands of times smaller than a human hair. It's just incredible.
And when you can write instructions on that tiny of a scale, you can do some truly unbelievable things. You can emboss millions of microscopic lenses to tell a solar cell to capture more light. You can create lab-on-a-chip devices for instant medical tests. You can even copy nature, embossing textures that mimic a lotus leaf to make a surface repel water, or that mimic shark skin to reduce drag. We're even starting to see reprogrammable and self-healing surfaces, all thanks to this tech.
So where does all this go from here? Well, the toolkit for embossing is expanding at an incredible speed, which is letting us not just shape materials, but grant them entirely new abilities, almost like superpowers.
I mean, just look at some of these next-level methods. Engineers are dreaming up new ways to do this because the old ones just can't keep up. You've got roll-to-roll embossing, which is all about speed and scale. It works like a futuristic printing press, churning out complex surfaces for things like flexible displays. And then you have laser-assisted methods, which are all about insane precision, using lasers to etch these impossibly detailed stamps for things like anti-reflective coatings.
And this really brings us to the single most important idea to take away from all this. Embossing has evolved. It's not just about making something look a certain way anymore. It's about fundamentally engineering its properties. We're no longer just creating a pattern. We are giving the material a detailed set of instructions. Be stronger. Repel water. Capture more light. At the end of the day, you can think of it like this. Embossing is letting us write information not just on a material surface, but into its very structure. It's a way of programming matter itself. And that, of course, leaves us with one heck of a fascinating question. What will we tell our materials to do next?